This is the third video of our study of substitution alpha to carbonyl compounds. And in it we are going to look at 1,2 and 1,4 additions to unsaturated carbonyl compounds. Specifically, we will be looking at nucleophilic addition to alpha-beta unsaturated carbonyl compounds, alkylation of alpha-beta unsaturated compounds, and finally at Robinson annulation. In the previous chapter, we have learned how to prepare alpha-beta unsaturated aldehydes and ketones in aldol condensation reaction. Now we are going to look in reactions of alpha-beta unsaturated ketones and aldehydes and other carbonyl compounds. Alpha-beta unsaturated carbonyl compounds have two electrophilic sites. So when we look at resonance structure of a typical alpha-beta unsaturated compound, and here is general formula, we can see that there is beta carbon that is an electrophile. So this middle resonance structure shows beta carbon as being an electrophile, electron deficient site, so a site that will react with a nucleophile. And this is shown also here with red arrow. Alternatively, this final resonance structure on the right shows carbonyl carbon as being electrophilic site. So this is the carbon that could also react with a nucleophile. So we have two possible sites that could react with nucleophiles. As you will see in a minute, the way we number atoms of an enone system, alpha-beta unsaturated carbonyl system, those two carbons are carbons 2 and 4 of the enone system. Carbonyl carbon is carbon 2 or atom 2 of the enone system, and beta carbon is atom 4. So reaction with a nucleophile proceeds in such a way that the nucleophile could end up attached to carbon 2 or carbon 4, shown here with red and blue arrows. So nucleophile adding to carbon 2 results in 1,2 addition, and adding to carbon 4 in 1,4 addition. 1,2 addition occurs when, of course, as I just mentioned, nucleophile ends up on carbon 2, and that means that electrophile proton will end up on carbon 1. So here is how we label atoms of an enone system. Enone means en, alkene, on, ketone. So alkene, ketone. Enone also is term used for example, alkene aldehyde or alpha-beta unsaturated aldehyde. So it's a generic term. So enone system has 4 atoms, and these are the 4 atoms of that system. Atom 1 is carbonyl oxygen. Atom 2 is carbonyl carbon. Atom 3 is atom of the alpha carbon atom of the double bond, and atom 4 is beta carbon atom of the double bond. Nucleophile could add to carbonyl carbon, and that means it ends up on the atom 2. Then in the workup, when we add dilute acid, alkoxide is protonated, so nucleophile and electrophile end up in the final product on atoms 1 and 2 of the enone. 1,4 addition is a little bit more complex, and it's called 1,4 addition because nucleophile and electrophile initially add to atoms 1 and 4, but they actually at the end up on atoms 3 and 4. So that may be a little bit confusing. So if you follow this, again we have 4 atoms of the enone system labeled 1 through 4. Now initial step proceeds as addition of nucleophile to atom 4. That results in formation of the inlet anion, here highlighted in yellow. Now protonation or addition of electrophile protonates atom 1, oxygen 1, and that is 1,4 addition. But this is an enol, this is unstable species, and enol tautomerizes, which means the double bond and proton exchange places, and in the final product actually proton ends up in position 3. Even though overall final addition is in the atoms 3 and 4, on the atoms 3 and 4, we still call it 1,4 addition because the actual addition proceeds in 1,4 fashion. The final step is tautomerization step, and we say it doesn't count. So, well, you need to know what is the final product and what is the outcome of 1,4 addition. The initial addition proceeds to atoms 1 and 4 of the Anion system, and the final product ends up with nucleophile and electrophile being of the atoms 3 and 4. Here are some examples of the additions. So here we have alpha-beta unsaturated ketone. Reaction with phenyl lithium followed by acidic workup results in formation of this alcohol. And that's 1,2 addition. This would be, if we want to name this alcohol, this would be 2-phenyl trans, this is trans alcohol, 3, so 2-phenyl or trans 2-phenyl 3-pentene 2-ol. This reaction of alpha-beta unsaturated ketone with sodium borohydride in presence of cerium trichloride in methanol results in also in 1,2 addition. So it results in effectively reduction of carbonyl group while double bond is left intact. In this case, hydride anion from sodium borohydride adds to carbonyl carbon to atom 2, and proton from methanol ends up on carbonyl oxygen, atom 1. Here are some examples of 1,4 additions. So 1,4 addition occurs when we have what we call a soft nucleophile. Soft nucleophile is nucleophile that is not charged and where charge is maybe possibly a bit diffuse. So nitrogen is not charged, so it's a soft nucleophile. Soft nucleophiles add in 1,4 fashion, so nitrogen atom adds to beta carbon of the double bond, carbon atom 4 or carbon 4 of the anion. Initial intermediate is ammonium cation. It is deprotonated to give enolate anion, then enolate anion is protonated, and it's actually protonated on alpha carbon to give result of 1,4 addition. Another example of 1,4 addition is cyanide anion. Cyanide anion counts as a soft nucleophile because charge is diffuse. Charge is shared by carbon and nitrogen atoms. So larger anions that has a diffuse charge count as soft. So nitrile adds to carbon 4. So here is in the middle cyclohexenone. And cyclohexenone can undergo either 1,2 or 1,4 addition. 1,2 addition occurs with what we call hard nucleophiles. Hard nucleophiles are the ones that have concentrated negative charge on atom that has low electronegativity, like carbon. Note that in case of methyl lithium, charge is concentrated on carbon, unlike cyanide anion in the previous example, where negative charge was shared by carbon and nitrogen atoms. Here, charge is concentrated on carbon atom. So this would be what we call a hard nucleophile. Small nucleophile where negative charge is concentrated on one atom. And so hard nucleophile undergoes 1,2 addition. So upon protonation, we have 1,2 addition. On the other hand, soft nucleophile would be Gilman reagent or lithium dialkyl cuprate. In this case, negative charge is spread over the whole anion. Lithium is positively charged cation, so dialkyl cuprate anion is the soft nucleophile, and addition occurs in 1,4 fashion. These two reactions are characteristic of organometallic compounds. So alkyl lithiums typically add in 1,2 fashion because they are hard nucleophiles, and lithium dialkyl cuprates add in 1,4. They are soft nucleophiles. Now, situation is a little bit more complex when we consider Grignard reagents, organomagnesium compounds. Typically, textbooks will say that organomagnesium compounds are hard nucleophiles and that they add in 1,2 fashion. And that is frequently the case, but unfortunately that's not always the case. In this particular example that we have here, they add indeed in 1,2 fashion. Organomagnesium compounds appear to be sensitive to steric hindrance and they add to least sterically hindered position. So it depends whether position 2 or 4 is less sterically hindered, they will add to that one. Now at this point, I just want to give you one practical tip. If you are taking an exam, standardized exam like MCAT or GRE, Graduate Recording Examination, and you encounter a question of this type where organomagnesium compound is adding to an enon, you should always answer that addition is 1,2, because that's what test makers expect you to answer, 1,2 addition. But as I said, situation is considerably more complex. And there are examples where addition occurs in 1,2 fashion, as in this case, 100%, or in 1,4 fashion, again, an alternative example, 100%. Most common case with addition of Grignard reagent is this one, highlighted in yellow, where we get mixture of 1,2 and 1,4 addition. For that reason, we actually don't use Grignard reagents anymore, or don't use them much anymore. We prefer to use organolithium reagents, which are consistent and give 1,2 addition, or we use organolithium dialkyl cuprates, which are also consistent and give 1,4 addition. Now we're going to look at addition to alpha-beta unsaturated compounds that results in formation of new carbon-carbon bond. That's Michael addition. And Michael addition is actually addition of enolate anion to an enon, to alpha-beta unsaturated compound. Enolate anion has negative charge that is delocalized. It's delocalized over oxygen and carbon atoms. For that reason, enolate anion is a soft nucleophile and always adds in 1,4 addition. It means that Michael addition is 1,4 addition. So here we have a brief review, 1,2 versus 1,4 addition. 1,2 addition is as a product shown on the left, 1,4 on the right. So Michael addition always involves 1,4 addition. Typically, Michael addition involves enolate anion that is generated from dicarbonyl compound. Again, in the previous video, we have seen not only how to make enons, but also how to form dicarbonyl compounds, like beta-ketoesters. Beta-ketoester is typical substrate for Michael addition. That's because middle carbon is activated by 2 carbonyl groups and is rather acidic. It's easily deprotonated, and once deprotonated, adds in 1,4 fashion to alpha-beta unsaturated carbonyl compound. So to deprotonate it, we use a base, in this case ethoxide, because it matches the leaving group of the ester. I hope you remember that from the previous video. And then the enolate anion adds to atom 4 of the enon system. You should practice drawing the products and identifying which bond is made in the product to draw the correct, so that you can draw correct product. In the next example, we have a diester, so beta diester that again adds to an enon, to alpha-beta unsaturated ketone. In the previous example, it was alpha-beta unsaturated aldehyde, now alpha-beta unsaturated ketone. Since this is dimethyl ester, we are using methoxide, like sodium methoxide, as a base. And again, product is result of 1,4 addition. In third example, we have a diketone as dicarbonyl compound, and addition is to alpha-beta unsaturated amide. So as you can see, variety of alpha-beta unsaturated compounds undergoes reaction. Since dicarbonyl compound is diketone, we have wider choice of bases we can use. So we can use hydroxide base, like sodium hydroxide, as in this example, or we can use various alkoxides. And again, product is result of 1,4 addition. Here are some other examples, some additional examples. So again, we have beta-ketoester, and then addition occurs to another unsaturated ester. This ester is a little bit complex, and there are 2 double bonds. Note that only one of the 2 double bonds is conjugated to the carbonyl group. The other one is isolated. So the other double bond does not undergo reaction and does not affect this reaction outcome in any way. Addition occurs again to atom 4 of the enon system, and here a little bit of a challenge is to identify that atom 4. Since there are two esters involved, they must have identical leaving groups. So both are ethyl esters, and of course base has to be ethoxide in ethanol. And next example again illustrates versatility of this reaction and variety of substrates we can use. So one of the activating group is nitrile group. So it doesn't have to be dicarbonyl compound. One of the compounds involved could be a nitrile. One of the two groups could be a nitrile. And then nitrile adds to carbon 4, in this case not of enone system but alpha-beta unsaturated nitrile system. In alpha-beta unsaturated nitrile, atom 1 is nitrogen, atom 2 nitrile carbon, atom 3 alpha carbon of the double bond, and atom 4 beta carbon of the double bond. And again, base is methoxide because ester, we have ester group. Ester is methyl ester, so base has to be methoxide. Note which bond is being formed. Where is the bond that is being formed? It's carbon that is between the two activating groups of the inlet anion, and addition is to beta carbon of the double bond. When it comes to mechanism, of course, deprotonation of the most acidic carbon, and that's one between the two carbonyl groups or between two activating groups in general, produces inlet anion. That inlet anion, as a soft nucleophile, adds to atom 4 of the enone system, and that results, so here is addition to atom 4 of the enone system, that results in formation of inlet anion, and inlet anion is protonated to give the final product. Michael addition has been exploited in a reaction sequence called Robinson annulation that is used to prepare 6-membered rings. This is one of the best methods we have besides Diaz-Alder reaction to prepare 6-membered rings. Annulation in general as a term means ring forming reaction, and so this is specific annulation, Robinson annulation. It exploits Michael addition followed by an aldol condensation to close a 6-membered ring. So a Robinson annulation starts with a carbonyl compound and deprotonation of carbonyl compound to form an inlet anion. In previous examples, all of the carbonyl compounds that generated inlet anions were dicarbonyl compounds. Those are preferentially used because it's easier to deprotonate them. It's easier to generate inlet anion. But we can use ordinary carbonyl compound such as acetone, simple ketone, and deprotonate it. Addition to an enone, this is commonly used enone, methyl vinyl ketone, or MVK. It's used a lot in organic synthesis, so addition to carbon 4 of the enone system results in formation of this inlet anion. Now, this inlet anion is actually an ion of diketone. And recall from previous video, in cyclizations of diketones like this, 3 and 4 membered rings and also 7, 8 cannot form. This inlet anion would actually close a 4-membered ring. Note that negative charge is on carbon 3 of the diketone. So that would close a 4-membered ring. That ring cannot close, so for that reason, inlet anion protonates to form, or is protonated to form a diketone, which is then deprotonated in position 1. Once it's deprotonated in position 1, a 6-membered ring can be closed. So now intramolecular aldol condensation occurs. So first step, initial addition was Michael addition, and now this is the second step that occurs intramolecularly within the same molecule, where aldol reaction occurs and 6-membered ring is closed. So carbon 1 with negative charge forms bond with carbon 6. So addition occurs to carbonyl carbon. Upon protonation, we end up with a ketol. So that's aldol reaction. And if we want to prepare alpha-beta unsaturated compounds, which is what we usually do, because those compounds are usually more useful, we will heat the reaction product or simply carry out this reaction with heating, and product will be alpha-beta unsaturated ketone or cyclohexanone. This type of reaction, Robinson annulation, has been exploited a lot in synthesis of natural products called steroids. So here, to synthesize basic steroid skeleton, we use somewhat more complex dicarbonyl compound. So beta ketoester. How we prepare these beta ketoesters was also covered in the previous video, and this particular one is result of Dickmann condensation. Deprotonation, of course, deprotonates carbon between the two carbonyl groups, and then addition to carbon 4 results in formation of this rather complex diketoester. And then in the second step, 6-membered ring is closed. Step is carried out with heating, so it is aldol condensation. So second ring is closed, and we have formation of these two rings. These two rings are actually, if you look at them carefully, rings C and D of a steroid. Now the entire synthesis of steroid skeleton, not just 2 out of 4 rings, is shown here. So we use carbonyl compound on the left, so ketone on the left, that has this little bit different synthesis. So ketone on the left, that is bicyclic, and it has only one alpha position on the 6-membered ring. So deprotonation and addition to carbon 4 of the enone system results in formation of this rather complex product, which undergoes intramolecular aldol condensation to give basic steroid ring. So the lettering of the rings in a steroid skeleton is that this first 6-membered ring, which is here aromatic, is ring A. One attached to it is ring B. Then one that has double bond and carbonyl group is ring C, and 5-membered ring is ring D. So that explains why in the previous case, in the previous example, I said that rings C and D were formed. So this 6 and 5-membered ring, 6-membered ring that corresponds to ring C, and 5-membered ring that is ring D of steroid skeleton were formed in Robinson annulation. So Robinson annulation is reaction that has been used a lot in the past in synthesis of natural products, particularly steroids. And this completes this third video on substitution alpha to carbonyls. And next, in the final video, we are going to examine alkylation of carbonyl compounds.